Hi everyone, welcome to today's video on direct variation. So what is direct variation? Direct variation describes the relationship between two things that are directly proportional to each other. For example, you're buying bananas and it costs $2 per banana. Then your total cost depends directly on the number of bananas you buy. So if you buy one banana, that would be $2 per banana times one banana for a total of $2. If you buy two bananas, that would be $2 per banana times two bananas for a total of $4. And if you buy three bananas at $2 per banana, that would be $2 times three bananas for a total of $6. We can model our total cost with the formula total cost equals $2 times the number of bananas that you buy. Our formula for total cost follows this general structure, y equals kx, where y is our dependent variable, k is our constant of variation or constant of proportionality, and x is our independent variable. This is the general formula for something that follows direct variation. If we were to graph our equation for total cost, it would look like a straight line where k is the slope. The slope tells us how steep our line is. Y would be our total cost. K, our constant of variation or proportionality or a slope, whatever you like to call it, would be 2. And x would be the number of bananas that we buy. So if x is equal to 0, so we don't buy any bananas, then our y is also going to be equal to 0 because 2 times 0 is 0. And we can see this in our graph as well. When x is equal to 1, we get 2 times 1. So our total cost would be 2. And we see this in our graph as well. When x is 1, y is 2. When x is 2, y is equal to 2 times 2. So y would be equal to 4. And we see this in our graph as well. When x is equal to 2, y is equal to 4. And so on. You can keep doing this with different values of x and then plotting your coordinates onto the graph. This arrow over here illustrates that this line continues infinitely. And the reason we don't see it extending in the opposite direction is because we can't have a negative x value in this scenario. That doesn't mean we can't in other scenarios, but in this scenario, it just wouldn't make sense because we can't have negative bananas. And just a note over here, the graph for direct variation always passes through the origin, and the origin is the coordinate 0, 0. And the reason for that is because if x is equal to 0, then y will also be 0 no matter what the k value is. Remember, direct variation follows this general equation y equals kx, where k is some sort of constant. So we can see down below that if x is equal to 0, so we plug in 0 in place of x, no matter what value this is, any number times 0 would equal 0, so y would automatically equal 0. So for that reason, if x is equal to 0, y must be equal to 0 as well, and that is why the graph for direct variation always passes through the origin. Now let's go over some examples. Consider the two equations a equals 2b plus 3 and a equals 2b, which is an example of a direct variation. So first remember, direct variation follows the general equation y equals kx, where y and x are variables and k is some sort of constant. Y is our isolated variable, which means it's by itself, whereas x is being multiplied by some sort of constant or number. In both of these instances, a is our isolated variable, so a would be our y in this case. B is our other variable that is being multiplied by some constant. So our constant is going to be 2, and our variable is going to be b. Therefore, the equation that is an example of direct variation is a equals 2b. So that would be this one over here. The one on the left is not an example of direct variation because of this positive 3. This positive 3 means that our a depends on two things. It depends on our b, which is a part of this term, but it also depends on our positive 3. Question 2 asks us to determine the constant of variation, so our k value, for each direct variation. So for part A, it says the distance traveled by a car varies directly with time. So the distance depends on the time. Since our distance is the thing that depends on something, it's going to be our dependent variable, so our y. And since our time is the thing that doesn't depend on anything, it's our independent variable, or our x. And it also says the car travels 320 kilometers in 4 hours. So we can set up our equation. Remember, direct variation follows the formula y equals kx. So if we want to isolate for k, we need to divide by x on both sides. That gives us k is equal to our y divided by our x. In this case, our y is our distance traveled, which is 320 kilometers. And our x is our time, so 4 hours. So k is equal to 320 divided by 4, which is equal to 80. We ignore our units here because this is the constant of proportionality, and we typically don't include the units in our equation. And we can check to see if this is correct by writing an equation and then plugging in 4 for our x and seeing if we get 320 for our y. Since at x equals 4, y equals 320, we know we did this correct. So we can move on. For part B, it says the total earnings varies directly with the number of tickets sold. 4 tickets cost $10. So first let's write out the equation for direct variation again. So y equals kx, and it's our total earnings that varies with the number of tickets sold. So since the total earnings is the thing that depends on the number of tickets sold, it's going to be our dependent variable. And the number of tickets sold is our independent variable, so it's going to be x. Instead of isolating for k and then plugging it in, I'm going to show you another way of how to do this. So I'm just going to plug in our values directly into this equation over here. So we have 4 tickets, so x equals 4, and the total cost is $10, so y equals 10. So we know 10 is going to be equal to k times x, which is 4 in this case. So to solve for k, we need to divide by 4 on both sides. The 4's would cancel out on this side, and k would be equal to 10 divided by 4, which is 2.5. And once again, to check, you can write out the equation. So y is going to be equal to 2.5x, and then you can plug in your x value and see if it spits out the correct y value. But I'll let you check that on your own. Question 3 says the cost C in dollars of buying yarn varies directly with its length L in meters. Part A says to find an equation relating C and L if 50 meters of yarn costs $125. So if it varies directly, we know it follows the equation y equals kx. In this instance, it's our cost that depends on the length of yarn that we buy. So our cost is going to be our dependent variable, and our length is going to be our independent variable. So we end up with this new equation, C equals K times L, where K is our constant. So we know that our length is equal to 50 meters, and we know that our total cost is equal to $125. So we can plug these into our equation to solve for K. To isolate K, we need to divide by 50 on both sides. The 50s will cancel out here, and then k is equal to 125 divided by 50, which is equal to 2.5. The question is not asking us to just find k, it's asking us to find the equation relating c and l. So we need to use our equation that has c, l, and k for our answer. So we can plug our k back into this equation over here to get our equation relating c and l. So from that, we get C is equal to 2.5 times our length of yarn, and that's our final answer. Part B says, what does the constant of variation represent? So first, let's look at our equation. So our total cost is equal to $2.5 times our length in meters. So what that means is, if our length is equal to 1, then our total cost is going to be equal to 2.5 times 1, or $2.5. If our length is equal to 2, then our total cost is going to be equal to 2.5 times 2, or $5. So as you can see, as our length increases by 1 meter, our cost increases by $2.5. And we can keep doing this. So if L is equal to 3, then our cost is going to be equal to $7.5. So another increase by 1 meter is going to be another increase in $2.5. So our constant of variation means that for every increase of 1 meter, our cost is going to increase by $2.5. Part C wants us to use the equation to determine the cost of 120 meters of yarn. Our equation is C equals 2.5 times L. So we want to determine the cost, so C is unknown, of 120 meters of yarn. So our length is equal to 120 meters. We can plug this into our equation to solve for C. So the cost in dollars is equal to 2.5 times 120, which is equal to 300. Therefore, the cost of 120 meters of yarn is $300. Question 4 says, consider the two graphs, which is an example of a direct variation. So remember, direct variation follows the equation y equals kx. So that means that if x is equal to 0, then y must also equal 0. That means that the straight line must pass through the origin. For graph A, we see a plot point at 0, 0, right here at the origin. For graph B, the line does not intersect with the origin. It intersects somewhere around here. This is a problem because it means that if x is equal to 0, y is not equal to 0. So that means there must be some sort of other part over here that is affecting y. So this would not be an example of direct variation, since direct variation means that y depends only on x and not any other factors. So in this case, the answer is A, as it's the only straight line that passes through the origin. Lastly, question 5 says, which of the following data sets shows a direct variation between x and y? Once again, the equation for direct variation is y equals kx. Based off of this equation for direct variation, we have two criteria that we need to meet. Our first is we have some sort of constant, or k, so that means as x increases by 1, y increases by the same amount. Our second criteria is that our line passes through the origin, so there must be a point at 0, 0. So following these two criteria, let's look at both of our data sets. In our first one, as we increase by 1 on the x side, we increase by 2 on the y side. And this pattern continues with the rest of our numbers. So as we go from 2 to 3, we go from 5 to 7, which is an increase of 2. And 3 to 4, which is an increase of 1, we go from 7 to 9, which is also an increase of 2. So it passes the first test. Now let's look at our second data set. As we increase by 1 on the x side, we also increase by 2 on the right. And this also continues. So this one also passes the first test. So if we're increasing by 2 on the y side with every increase of 1 on the x side, that means our k value would be 2. So if our data set shows a direct variation, it would have to follow this equation. And since both of our data sets show this increasing by 2 trend, they would both have to follow this equation. So these are our potential equations for each of the data sets if they follow a direct variation. If our data sets follow these patterns, which we know is the pattern for an equation that has a direct variation, we know that it will already pass through the coordinate 0, 0. So we know that both of these already passed the second test. Now all we have to do is make sure our data sets follow these patterns for direct variation, and if they do, then they will show a direct variation, and if they don't, then we know that it does not show a direct variation. So if I plug in x as 1, I should get 3 as our y value. And for this data set, if I plug in x is equal to 1, I should get 2 as our answer. So for our first one, let's test it with x equals 1. So for this one, if x is equal to 1, y is equal to 2. This is not the case, so this data set is not an example of a direct variation. And we can test this with other x values as well. So let's do it with the next one. If x is equal to 2, then we get y is equal to 4. So if x is equal to 2, y is equal to 4. And that is also not the case. So this is also not an example of direct variation. And you'll see that is true for the other points as well. Now we can do the same thing with our other data set. So our other data set should follow this equation for direct variation. So let's test it out. So if x is equal to 1, we get y is equal to 2 times 1, or y is equal to 2. So for x is equal to 1, we get y is equal to 2. And that holds true with our data set. Now let's test the next one. For x is equal to 2, we get y is equal to 2 times 2, or y is equal to 4. So if x is equal to 2, y is equal to 4, and that holds true with our data set. And you'll find that to be true with our other values as well. And we can also check to see if 0, 0 would be a coordinate, and if we plug in x as 0, we will get y is equal to 0 as well. So only the second data set would be an example of direct variation. And that's it for today's video. I hope you guys liked it. Let me know what you want to see next in the comments below, and I'll see you in the next one.